Hello, this is Mrs. Sargent, and this is lesson 6.6, types of reactions, and today we're going to talk about single and double replacement reactions. So a single replacement reaction is going to occur when a metal is going to replace another metal, or a non-metal is going to replace another non-metal. The general equation is chemical A reacts with chemical BC to produce chemical AC and chemical B. So think about it like this. In our last lesson, I talked about synthesis, and you worked your magic of your best pickup line on your crush to get a date for Valentine's Day. So now you have that date, and you're at a dance or you're at a party, and you're dancing with your date, and someone taps you on the shoulder and then cuts in. So one person was a loner and you had a couple. That loner cut in, and now we have a new loner and a new couple. The same thing is going to happen with our chemicals. And we're going to use the activity series. The activity series is located on the back of your periodic table and on the right hand side. And you just have this portion here. But if you want to write at the top that the most reactive is on the top end of it, and then the least reactive is on the bottom end. I'm perfectly fine with you going ahead and labeling that on your periodic table. You might also want to draw an arrow showing increasing reactivity. So we use the activity series in order to predict if a single replacement reaction will occur. The reactant that stands alone must be more reactive than the element it is trying to replace, meaning that it needs to be higher on the list on your activity series. So, our first example, we have iron is added to a solution of calcium chloride. Iron is our element standing alone. Iron is a metal, so it's going to replace a metal in calcium chloride. Calcium is the metal there. Chloride is the non-metal. So we're going to find iron, and we're going to find calcium. In order for iron to kick calcium out of its place, iron has to be more reactive. Well, iron is less reactive because it's lower on the list, so this reaction does not occur. So then you're going to write no reaction. Also, acceptable ways of writing no reaction is no RXN or NR. Any of those are acceptable answers, but you can't leave it blank because then I think that you just haven't even looked at it and tried it. But if you tell me there's no reaction, then I understand that you know why there is no reaction. In another situation, we have calcium that is added to a solution of iron 2 chloride. So calcium is standing alone. We're adding it to a solution of iron 2 chloride, so that's going to be FeCl2. So we want calcium to kick iron out of this compound. These are the same two elements that we were looking at here. Calcium is higher on the list, so this reaction will occur. So we're going to put calcium and chlorine together. So calcium is a 2 plus, chlorine is a 1 minus. So this is going to be CaCl2. And iron is now standing alone. So then you need to go through and balance it. You have 1 calcium in your reactants, 1 iron, and 2 chlorine. In your products, you have 1 calcium, 1 iron, and 2 chlorine. So this is balanced. Just go back and put 1s in for your coefficients. So zinc, solid zinc is going to react with 10-2 chloride. We need to look on our activity series and find 10 and zinc. Zinc is here, and 10 is here. Zinc is the one standing alone, so zinc is going to kick 10 out of 10-2 chloride because it stands alone. Zinc is a 2+, chlorine is a 1-, so our formula is going to be ZnCl2. And then we're going to have 10 out by itself. So then we need to go through and balance this. And it is already balanced, so then we just need to go and fill in with 1s. If you Google floating tin sponge, you will find a video of this reaction. What happens is you put solid zinc in the bottom of a beaker, you add the 10-2 chloride, immediately bubbles start forming, indicating you have a new gas being formed in a chemical reaction. The zinc is the 10 is gonna form crystals on the zinc, and then end up replacing it, and then eventually it's going to become less dense. The hydrogen bubbles are going to create cavities, making it less dense, and then the 10 is going to float to the surface. In thermite, we have iron 3 oxide reacting with aluminum. And we watched a video earlier in the year of thermite, something that the AP Chem kids did. So aluminum wants to kick iron out of the way. So we need to look back here and find iron and then aluminum. Aluminum is higher, so the reaction will go. So we're going to have aluminum oxide. Aluminum is a 3+. Oxygen is a 2-. So we're going to have Al2O3 for our formula. And then iron is going to be by itself. Then we need to go through and balance this. In our reactants, we have 2 iron, 3 oxygen, and 1 aluminum. In our products, we have 1 iron, 3 oxygen, and 2 aluminum. So in order to balance this, we need to put a 2 in front of iron and a 2 in front of aluminum. Now we're balanced, and go back and fill in with 1s. So here is a video of thermite.
This is thermite. It's a powdered mixture of iron oxide and aluminium, which when ignited burns at 2,500 degrees Celsius, which is very, very hot. This is liquid nitrogen. It's specially stored at minus 198 degrees Celsius. That's 163 degrees colder than the North Pole in winter. But is it cold enough to neutralize the intense heat of thermite? Packed into the slow-release mechanism of a garden flower pot, the Thermite is ready for action. Just like the touch paper, stand well back. The fuse triggers the irreversible Thermite reaction. As scorching hot meets freezing cold, a fierce battle rages. The smoke clears, and incredibly, nothing remains. As the Thermite burns at 2,500 degrees, it releases a raging torrent of molten iron, which rains down upon the liquid nitrogen, boiling the glacial mixture away in a plume of vapour and melting the cylinder, leaving just a puddle of white-hot iron. A clear victory for Thermite. So there you go, Dan. Adding something cold to Thermite doesn't cancel it out. It just makes it angry. Thermite. You won't like it when it's... This is a car. It's been specially chosen to be destroyed because it's old, it's white, but more importantly, because it's French. The engine block is the densest part of a car. It's basically a huge lump of metal, and, well, it's very hard to melt. Lucky then, the Brainiacs have plenty of Thermite, specially packed into the slow-release mechanism of a garden flower pot. A big pile on the bonnet directly over the engine block should do the trick. Time to light the fuse and give this homage to French engineering the send-off it so richly deserves. The irreversible Thermite reaction begins. Within seconds, the fiery concoction eats through the bonnet, spraying molten Thermite into the engine beneath. The devastation continues inside until finally a torrent of white-hot liquid metal pours out of the bottom, signaling the inevitable victory for Thermite. A quick check confirms a clear path of destruction through the engine. Now that the engine is melted clear...
So that's some Thermite reactions for you. Take a look at these three single replacement reactions. Go ahead and pause the video and try them on your own. Welcome back. Magnesium stands alone. It's a metal, so it's going to want to kick out copper. So magnesium is a 2+, and nitrate, I'm so sorry, tongue-tied there, NO3 is a 1-, so our formula is going to be Mg NO3 2. And then now we're going to have copper standing alone. We need to go through and we need to balance it. We have 1 magnesium, 1 copper, and 1 nitrate. In our reactants, in our products, we have 1 magnesium, 1 copper, and 2 nitrate. So we're going to have to put a 2 in front of copper nitrate in order to balance out our nitrate. And then we're going to need to put a 2 in front of copper in order to balance this out, and then go back and fill in with 1s. In the next reaction, we have sodium iodide and bromine. Now, we don't have one single element, but we have a single type of element here in bromine. Bromine is a nonmetal, so bromine is going to want to kick out another nonmetal, which is going to be iodine. You got to take a look at your activity series. Bromine is higher than iodine, so the reaction will occur. So we're going to have sodium and bromide in a compound. So sodium is a 1+, bromine is a 1-. So we only need one of each of those, NaBr. And then we're going to have iodine out by itself, but iodine is a diatomic, so we need 2 of those. So now, sodium 1, iodine 1, bromine 2. Over here in the products, sodium 1, iodine 2, bromine 1. So in order to balance out our iodine, we're going to need to put a 2 there. That's going to give us 2 sodium, 2 iodine. To balance out our bromine, 2 in front of sodium bromide. That's going to give us 2 sodium and 2 excuse me, bromine. And then we have tin and zinc chloride reacting. Tin is a metal, so it's going to want to kick out zinc. We're going to look at our activity series. And then here is tin. Here is zinc. Tin is not higher than zinc, so no reaction will occur. Oops. So that is single replacement reactions. In a double replacement reaction, the cations, which are positive, are going to trade places. One of the products must be a solid, a liquid, or a gas. Most of the ones that we're going to be working with is going to be a solid and then an aqueous. So the general equation is chemical AB reacts with chemical CD to produce chemical CB and chemical AD. So think about it like this. You're at that dance with your best friend and your dates, and for one song, you switch partners, and this is what's happening. You have 2 couples, you switch partners, you have 2 new couples. You can also think about it like square dancing. Switch your partner and do-si-do. So solubility. To be soluble means that it is going to dissolve in water. And when we dissolve in water, we have a solution, which is going to be an aqueous state of matter. Insoluble does not dissolve in water. And so this is going to be a solid. On the back of your periodic table, you also have this rules for solubility of common ionic compounds in water. The anion is in the left column, which means that this is negative. The cation is in the center column, positive. And then over here you have your state of matter. Okay, so how you read this chart, if you have any of these as your negative ion in a compound, and it is bonded to any positive ion, it's going to be aqueous. In this next line here, chloride, bromide, or iodide, any positive ion is going to be aqueous, but if it is paired with silver, lead, or mercury, it's going to be solid. Fluorine, any positive ion is going to be aqueous with the exceptions of magnesium, calcium, strontium, barium, and lead. 2+, those are going to be solid. Sulfate, any positive ion is going to be aqueous except for strontium, barium, and lead. Those are going to be solid. Sulfide, any positive ion is solid except for group 1 and 2. So anything in the 1A or the 2A group and ammonium, those are going to be aqueous. Hydroxide, oxide, carbonate, phosphate, and chromate. Any positive ion is going to be solid with the exception of group 1 metals and ammonium. Those are going to be aqueous. So this is how this is going to work. Remember that in a double replacement reaction, the cations are going to switch places. So the metals are going to be the ones that are going to be looking to switch. So we're going to switch lead and potassium. So we need to write out for lead iodide. Lead is going to be a 2 plus because nitrate is a 1 minus. So Pb 2 plus with iodine 1 minus. Our formula is going to be PbI2. And then we're going to take a look back at our solubility chart. Iodine, any positive ion is aqueous with the exceptions, and lead 2 plus is there. So this is going to be solid. And then we're going to have potassium and nitrate bond together. So potassium is a 1 plus. Nitrate is a 1 minus. We only need one of each of those. Take a look back. Nitrate, any positive ion, it's going to be aqueous. This is a good thing because if you remember, I said one of your products needs to be a solid. So according to our solubility rules, your products, you need one aqueous and one solid. If you do not have this, the reaction will not occur. So you're going to write no reaction just like we did the single replacement. Basically, you can't have two aqueous solutions as products. So now we need to go through and balance this. Lead, we have 1. Nitrate, we have 2. Potassium, we have 1. Iodine, we have 1. Over here, lead, we have 1. Nitrate, we have 1. Potassium, we have 1. And iodine, we have 2. So in order to balance this out, if we put a 2 in front of potassium iodide, now our iodine are equal, but potassium and nitrate are unequals. Then we're going to put a 2 there to balance this out. And then we're going to go back and fill in with 1s. Go ahead and pause the video and take a look at these two double replacement reactions. Welcome back. We want sodium and copper to switch places because those are our metals. Those are going to be our positive ions. So we're going to put sodium with chlorine. Sodium is a 1 plus. Chlorine is a 1 minus. So that's going to be NaCl. Take a look back to see what is our state of matter. So chloride, any positive ion is aqueous with the exception of silver, lead, and mercury. Well, it doesn't fall into the exception, so it's going to be aqueous. And then copper is going to form a compound with hydroxide. Hydroxide is a 1 minus. We know that chlorine is a 1 minus, so copper has to be a 2 plus. So our formula is going to be CuOH2. Then we're going to look back at our solubility rules. Hydroxide, any positive ion is solid except for group 1 metals or ammonium, where we don't fall into the exception. So this is going to be solid. So our reaction will go. Then we need to go ahead and balance it. We have 1 sodium, 1 hydroxide, 1 copper, and 2 chlorine. In our reactants, in our products, we have 1 sodium, 2 hydroxide, 1 copper, and 1 chlorine. So we are unbalanced. In order to balance this out, we're going to need to put a 2 in front of sodium hydroxide. That's going to give us our 2 hydroxides, and then we're going to need to put a 2 in front of sodium chloride to get our 2-chlorine. Now everything is equal. Go back and fill in with 1s. In the last example we have here, we have aluminum sulfate and potassium hydroxide. So we want aluminum and potassium to switch places. Aluminum is a 3+, and hydroxide is a 1-. So our formula is going to be AlOH3. Take a look back. Hydroxide, any positive ion is a solid except for group 1 and ammonium, so this is going to be a solid. And then we're going to put potassium with sulfate. Potassium is a 1+. Sulfate is a 2-. So this is going to be K2SO4. Take a look back, find sulfates. Any positive ion is aqueous with the exceptions of strontium, barium, and lead. Well, we don't fall into the exceptions, so this is going to be aqueous. So our reaction will go. Now we need to balance it. 2 aluminum, 3 sulfates, 1 potassium, 1 hydroxide in our reactants, our products, 1 aluminum, 1 sulfate, 2 potassium, and 3 hydroxide. So we need to put a 2 in front of aluminum hydroxide. That's going to give us 2 aluminum and 6 hydroxide. Then we need to put a 6 in front of potassium hydroxide. It's going to give us 6 potassium, 6 hydroxide. And then we're going to need to put a 3 in front of potassium sulfate. That's going to give us 6 potassium and 3 sulfate. Now everything is equal. We're going to go back and put in a 1. And that is now balanced. So you need to take a look at the practice for single and double replacement reactions, as well as identifying the types of reactions. In the next class, you will have a homework quiz over all of the 5 types of reactions. So, combustion, synthesis, decomposition, single replacement, and double replacement reactions. You're going to have to go from word to skeleton to balanced, and then identify the types of reactions. If you have any questions, if you're still having trouble with writing your formulas, or balancing, or anything else that we've talked about, you need to come in and see me and get help. This is not going away. You are going to be using this the rest of the semester. Thanks for stopping by. Have a great day.